So there's a huge list of that's the operating systems, but there's also a huge list of hardware architectures that we support, and we have special bits of machine code and things tuned to run on these different chips. Obviously, the main one is x86. ARM is another really important architecture that is getting used more and more. And then there's kind of all the rest. And some of these are very old and really kind of belong in a museum. Some of them still have active users and are still developed. Power, for example, is used. Some people really like Power, and there's modern Power chips being developed that are very powerful. There's one interesting architecture that we don't have in our build farm, and that's RISC-V. If anybody's interested in RISC-V and would like to contribute to Postgres, it would be really cool to have a machine running Linux or FreeBSD or anything else on RISC-V building Postgres. That would help us learn how to program the thing and how to figure out the machine code for the spin locks and all that kind of stuff. All right, so probably the most difficult port that was done of Postgres was onto Windows, which happened back in 2005. That was Postgres version 8. And that was really a strange one because Windows doesn't have fork. So, the whole design of Postgres is a classic old school Unix program that has a parent process we call it the postmaster, and then it forks child processes to do all the work. But you can't even do that on Windows. So like the most basic thing about the way Postgres works needed to be done in a different way. So on Windows, we have this thing which executes a child and then tries to attach shared memory at the same address, which is a little bit different. And there's actually a whole lot of simulations of Unix stuff done for Windows to make it work on that operating system. Okay, so I did a whole lot of work on hash joins in Postgres and parallel hash joins in particular. And that, while I was doing that, I pretty soon noticed that FreeBSD could run parallel hash joins much faster than Linux. And it took me a while to figure out exactly why. And it comes down to the way huge pages or super pages, or also known as large pages, are done on these different operating systems. So when you have the way computers manage memory, virtual memory systems use pages of different sizes. And traditionally, the pages were always 4 kilobytes in size on Intel CPUs. But you can use these larger pages, which cause the virtual memory hardware to do less work. So you have this translation look-aside buffer thing. And I'm not going to go into the details of that, but you probably already know what I'm talking about. But the thing is, on FreeBSD, and maybe some other operating systems, the operating system does a really good job, or at least a pretty good job, of automatically using large page sizes for Postgres and the main shared memory areas and all of the temporary shared memory areas that we use for parallel query execution. But on Linux, that just doesn't work. At least it doesn't work by default. You have to go and turn it on in various ways. And there's this transparent huge pages feature on Linux. And I don't know all the reasons in detail because I just don't really understand how that thing works, but it doesn't seem to work very well with Postgres. It seems to not do a good job at actually using huge pages, and it doesn't, while it's trying to do it and failing, performance is terrible. So almost everybody recommends turning that off on Linux, or not turning it on, depending on your distribution. I think some have it on and some have it off by default, I'm not sure. But in Postgres, what we do is, for the main shared memory area that holds sort of the main buffer pool and so on, we tell the operating system that we would like that to be in huge pages if possible. And that works pretty well. But then when running parallel queries, we create extra bits of shared memory for parallel query temporary data. And that stuff doesn't go into huge pages. And the result is actually measurably slower. I mean, I can actually show hash joins running 30% slower as a result of that. And that turned out to be the reason why FreeBSD on exactly the same hardware would always run these particular queries faster than Linux. Now you can tune a Linux system to get that to work properly, but it involves some slightly tricky stuff, and it's not very widely known. I think probably in future they'll fix that. They'll probably make the transparent huge pages thing work better. I'm not really tracking that, so I don't know. But so that's a pretty interesting difference. Now on other operating systems like Windows and others, we can also use huge pages by explicitly asking to do so. But yeah, the configuration is a bit trickier. So yeah, that's kind of interesting. Another thing that you can do with huge pages is put the text segment, the actual code that's in the executable binary, into huge pages, and that on its own can make Postgres benchmarks run 5, 6, 7, 8% faster in some cases, which is, I think, pretty interesting. It's quite tricky to make Linux do that at all. I suppose in future they'll figure out how to make the transparent huge pages feature do that. But on FreeBSD, it just sort of works. Although a paper just came out quite recently, which I've put an asterisk at the bottom of the slide there, you can see the name of it, which shows that there are further improvements that could be made to improve that. So yeah, I think that's quite an interesting difference. And it shows that there's, whichever operating system you're using, there's quite a few things that you could tune that would really impact performance. Okay, so another thing that I figured out while comparing Linux and FreeBSD in particular is that sometimes when you do things that are kind of arbitrary, like Postgres, when it's doing hash joins, it allocates a lot of 32 kilobyte buffers, but each buffer has a small header at the start of it, which makes it slightly more than 32K. It's like 32K plus a few bytes. I can't remember how many, but not many. And it turned out that each operating system behave differently when you do that. On Linux systems where you have glibc as the libc, it's okay with that. It packs. You have a whole lot of requests for 32K plus a few bytes, and it handles that very nicely without wasting much memory. But on JEmalloc, which is FreeBSD's libc, the 32 kilobytes plus a little bit gets rounded up to 40 kilobytes. So you're wasting all this memory. So if you're, and it might allocate many thousands of those buffers. So the total amount of wasted space, which is 25% more memory, really sucks. So that was quite an interesting discovery. And I found that other operating systems had similar effects. glibc also does the same thing. It just doesn't do it at that size. If you get to a slightly larger size, it starts rounding things up. But at that size, it doesn't do this big rounding. So that was kind of interesting, an interesting discovery, and that's something I need to fix it somehow. I'm not sure how yet, but I'll fix it. So moving on to storage and buffered I/O. So one thing that we dealt with in the Postgres community a couple of years ago now was when we figured out that fsync didn't behave the way that we expected on Linux in particular. So the question is, so on Postgres, we use buffered I/O. So everything we write to disk, we use the write system call or the pwrite system call, and it goes into the kernel's buffers. And then at some point, the kernel decides to write it back, or we force it to write it back by calling fsync. And that means that we know that everything we've written is now down on the disk. So the question is the first question is, what should you do if fsync returns an error? If it tells you EIO, there was an IO error, perhaps your disk is broken, or perhaps if it's some kind of network storage, in the case of NFS, it can tell you there's no space when you call fsync, which is kind of weird because that's quite late to tell you that, but that's the way it works. But in some modern storage stacks, there could be all kinds of virtualization going on. There could be an error that is really a kind of network error, or is to do with some provisioning system where there's over provisioning or there's a delay while some space is allocated. And then, so the question is, what do you expect the kernel to do if it's told you that there was an error when you called fsync? And the answer surprised us in the Postgres community when we realized that each operating system was doing something quite different. And in the case of Linux, it would take all the dirty buffers that you had written to, that were in the kernel's buffers, and just throw them away. And then if it was a transient error because of some unusual storage stack that you're using, and then later on you even though the write was successful and the fsync returned an error, and then another fsync, because if you expected to be able to retry that fsync, that's the question. Should you expect to be able to retry it? Postgres believed in the past that you could retry it, so it would log an error and then it would retry a little bit later, and then it would get a success return code, but actually no data had been written back. Whereas FreeBSD and also some other operating systems, I think probably Illumos and Solaris, but I'm not 100% sure. If it couldn't write the data back to disk, then the data would still be considered dirty. So then it wouldn't, if you called fsync again, it would probably return an error again. Or if it returned success, that would mean that it really did succeed. So that was a fundamental difference. And there was another question, which is, if you've opened a file, written to it, and then closed it, and then you open it again, or some other process opens it again, and then calls fsync. But in between those two times, while nobody had the file open, if the kernel tried to write the data back to disk and that failed, doesn't have to tell you. And how should it tell you? The answer to that turned out to be different on different operating systems. And essentially, Postgres believed that things worked the way that FreeBSD works. I don't know if that's by coincidence or if that's because people who made those choices were using FreeBSD or some BSD. I don't actually know, but we finished up having to make some changes. We finished up having to make some changes to Postgres to remove that assumption from the design, so that now if there's a write-back error reported by fsync, we panic because at that point the world has gone insane. We have no idea what data is in the kernel and what data is gone. So the best you can do is crash recovery or restore from backups or something like that. So that was quite an interesting case of strange variations between operating systems that you can't really find actually in a manual. There's no manual that explains this, or there's no man page, for example, that explains any of this. Another interesting difference between operating systems is the way prefetching works. So because we're using buffered I/O, Postgres generates a stream of reads for 8 kilobyte blocks, but we kind of hope that the kernel is going to notice that we do that and start issuing larger read IOs to the storage hardware, maybe 128 kilobytes or some other size. It's going to realize that we're reading sequentially and start reading ahead of us so that our reads become instant. They don't have to actually wait for anything. That's kind of the goal, right? But there's some funny cases. In parallel sequential scans, Postgres has many worker processes, and they all they take turns at claiming the next block from a shared memory counter. So together they're all reading sequentially, but each process is actually reading with a step of maybe a few blocks. So the question is, does the kernel think that is sequential access or not? From its point of view, each process seems to be reading maybe block 1 and then block 8 and then block 12 and then whatever. And some kernels consider that to be sequential and some do not, which turns out to have a very big performance impact. So Linux, for example, when you do a parallel sequential scan, as long as the blocks that each process reads are less than 128 kilobytes apart, it considers it to be sequential. And then it's able to generate some nice large IOs and do nice read ahead for your sequential scan. Excuse me. But FreeBSD on UFS doesn't think that's sequential access. It only thinks it's sequential if you're literally reading block 1, then block 2, then block 3. Excuse me. But ZFS seems to be much smarter. I don't actually know exactly why exactly how it works, but it doesn't seem to have that problem. So maybe what Postgres is doing is really stupid, and UFS is being completely sensible, or maybe that's something that UFS should learn how to detect. I don't know. I'm not sure if I'm brave enough to go and write UFS patches, but that's a potential area to work on. Another question is, if you have two streams interleaved so that a single process is reading sequential blocks and also writing sequential blocks n blocks behind, then it will kind of look like a zigzag pattern. One question is, should the kernel consider that to be two sequential streams or just random access? And the answer for both Linux and FreeBSD UFS is that it thinks that that's random access, so performance is terrible. So that's something that could be improved on the operating system side. And once again, ZFS doesn't seem to have this problem, so it has some kind of deep magic that can recognize streams without. I literally don't know how that works, but in some magic way. So that's about prefetching heuristics, where the kernel looks at what you're doing and tries to figure out what you're going to do next and makes that more efficient, which is obviously what we want. There's another kind of prefetching, which is when you tell the kernel what you're going to be doing. And that's for cases where it's not very predictable. For example, if you're reading sequentially through the blocks of a file, it's pretty obvious what you're doing. But if you're following, if you've got some index which told you that there's like 100 different blocks on the disk that are scattered all over the place that have the data you want, you know you're going to read those 100 blocks, and you could tell the kernel to start reading them in advance and then read them. And hopefully by the time you issue the reads, they'll already be in the kernel's buffers. That's kind of the idea of the POSIX fadvise will need hint. So how well does it work? Well, I discovered that although it works really nicely on Linux, FreeBSD completely ignores it, as in fact do almost all the operating systems I looked at. So that's an opportunity to improve. Well, I would be interested in improving FreeBSD in that area, but many operating systems seem to lack that, because POSIX says that it's only a hint and it's a valid implementation to do nothing at all. And it seems a lot of operating systems went with that plan. I actually tried sometime around Christmas. I had some spare time and I tried to get ZFS to understand POSIX fadvise will need. And I was told that to get that patch into ZFS, my mentor told me, you should probably go and make it work for ZFS on Linux, because if you're just getting it to work for ZFS on FreeBSD, but since ZFS is actually now merged into a single repository, OpenZFS, and that's if you want to propose one of these features for OpenZFS, you kind of need to make it work on those two operating systems. So I'm kind of a little bit stuck figuring out how to get it to work exactly on Linux, because I'm not that used to working in the Linux source tree or with Linux concepts. So yeah, but I have something that basically works. It just needs some improvement. I don't know if anyone's interested in looking at that or helping out or making some suggestions or whatever. But that's a kind of a side project. All right, so the opposite of, so that was about reading and telling the kernel what you're going to be reading soon so that it can help get the data into cache before you need it. Kind of the opposite operation is telling the kernel that you're going to be syncing a file soon and that it should start writing it back to disk so that when you eventually call fsync, maybe it's going to be fast. You can get the same effect by tuning your operating system so that it always writes stuff back really quickly to disk. But maybe you don't want to write all files back quickly. Maybe you only want to write back some files because those are the files you're going to be fsyncing. So for example, if you have many different things, not just Postgres, but other stuff running on your server, maybe you'd want some stuff to be written back more eagerly or more lazily than other stuff. And even within Postgres, you might have temporary files that never need to be fsynced, temporary tables or something like that, or temporary data of various kinds. So Linux has a system call for that called sync file range. And as far as I can tell, no other operating system has anything like it, which means that they're kind of missing out on this opportunity to control the write-back speed in a more accurate way, which is quite nice. I've been wondering what it should be called. I think POSIX fadvise will sync would make sense, maybe. I don't know. I'm not entirely sure, but it's something that it would be cool if other operating systems could do that. All right, so I've talked about some things where Linux in my opinion, was less good, and some cases where it was, where it was worse, and in some cases where it was better than my favorite operating system. And this is the case where it's better. All right, so I was talking about prefetching, telling the kernel what you're going to need soon. That's actually a kind of poor man's version of asynchronous I/O. Real asynchronous I/O would be where you say, hey, kernel, please start loading this bit of a file into this bit of memory, please, and then tell me when it's done. But meanwhile, you can go and do something else. So eventually, comparing that to using the will need hint followed by a read, the difference is that in both cases you needed to know ahead of time what you're going to be reading soon, and then finally you read it. But in the case of true asynchronous I/O, you give it the buffer to write the data into, so that when it finally tells you that, and then it tells you when it's done. So at that point, there's nothing more to do. You don't have to copy it out of a kernel buffer into a user buffer or anything like that. So it's a bit more efficient. The trouble with true asynchronous I/O is that the way it works on every operating system is completely different. So, I mean, there's this POSIX AIO API, but Linux's version of it is not really good enough for us in various ways. There's kind of two different versions of it used on Linux, and one of them's non-standard, and the other one is an emulation with loads of threads. And we don't really want to use either of those. But there's a really interesting new thing called IO uring, which provides a very nice way to do a whole bunch of IO operations without even making system calls, just by pushing requests into a ring buffer and reading responses from a ring buffer. That's a brand new thing, which looks really interesting, and it might be that we can use that to build a asynchronous IO for Postgres in the future. But then we also need to work on other operating systems, and the other operating systems all do it very differently. Windows has got a completely different model. For FreeBSD and other Unixes, you would probably use POSIX AIO. So one of our jobs will be to come up with some kind of abstraction which works for all of these things and make it work. The other thing is direct IO, so completely skipping the kernel buffers. So a lot of the problems I talked about before, particularly the stuff about fsync and errors, that goes away if you take control of buffering yourself. But now you have other problems, because even though there are some things the kernel's doing that we don't like, it's actually doing a lot of things that we do like all of the, you suddenly need to have all kinds of worker threads to do read ahead for you and to do write back and so on. And there's some complexity to do it well. But that's something which I think we'll eventually do as well. Excuse me. But in both of these cases, asynchronous I/O and direct I/O, they'll probably always have to be options, because there's always going to be file systems that don't support non-buffered I/O, like ZFS, for example. And there'll probably always be operating systems that we don't have an async implementation for. So that's some work that's probably going to be coming up in the next couple of years to improve the I/O performance of Postgres. One historical note that I put in the first couple of bullet points there: when Postgres was created, there was no direct I/O or async I/O. Those things are not even really that old, or at least widespread adoption is not really that old. I think I'm just speculating. I'm not 100% sure, and I haven't asked any of the people involved because I don't know them. But I think that fsync might even have been added to BSD, to 4.2 BSD, because the Postgres people wanted it. Because it seems to have popped up around the same time as those people were active. I could be wrong about that. But, they were certainly at the right time in the right place to be having that conversation. It was 4.2 BSD that invented fsync. Before that, I actually don't know how anybody did reliable storage, because there didn't seem to be any kind of barrier, like any way to know that your buffer data had hit the disk. So before that time, I don't know, did did they just keep the power on all the time and hope it wasn't going to shut down? I don't know the answer, but all right. So another interesting difference between operating systems is that some have a facility for telling you that your parent process has died. Originally, the first system that I know of that had that was IRIX, and Linux copied that from IRIX, and FreeBSD. I wrote a small patch for FreeBSD to add that to FreeBSD, which is it's very simple. Just gives you a signal when your parent process dies, which actually saves a lot of effort. It's actually really quite difficult to find out when your parent dies. I mean, it's not conceptually difficult. I mean, the usual trick is to have a pipe, and when the other end goes away, you know that the process on the other end, if that was your parent, must be gone, and that works. But the problem is that if you want to know quickly when that happens, you finish up polling that thing quite a lot, and that was actually a source of performance problems until we introduced this parent death facility signal-based thing. So it would be cool if other operating systems had that as well. If other BSDs adopted a parent death signal, that would be quite neat. Yeah, and I wanted to say that just as we have to emulate fork, we also have to emulate Unix signals to make Windows work for Postgres on Windows. All right, so quite often Postgres is waiting on file descriptors. Idle backend processes waiting either on a socket connected to a client connection. There's also a self pipe, which is a standard Unix trick for dealing with signal handlers. And then there's this pipe connected to the postmaster so that you can know if the postmaster process has died. That's so that if somebody kills the postmaster, the entire tree of processes will disappear quickly. Because before somebody introduced that, it used to be that there were ways the system could crash and then leave all these funny processes all over the place, and it was really hard to kill them all. So that design is quite tidy, but when we were using poll, that worked pretty well on small computers, but using poll on really big computers with particularly multi-socket systems, where there's this one pipe that every process is holding onto one end of it, or a duplicate of one end of it, then it creates all this stampeding locks, lock contention in the kernel. And so we found that big systems were spending they were using a lot of system time. So on Linux, we switched to ePoll, and just recently for the BSDs and macOS, we switched to KQ, which is going to come out in Postgres 13, which will be in a few months. For all the other Unixes, we still use poll, and for Windows, we use Win32 stuff that does the same sort of thing. All right, so the KQ patch I added because people complained that they had very large database servers, which they moved from Linux to FreeBSD, and they found that they were using way more CPU, and that was the trigger for me to go and take this experimental KQ patch and realize that was the solution to that problem, and it works pretty well. So that hasn't come out yet, so we'll see. Another really interesting difference between platforms that I ran into recently was that what happens when you've got a protocol where both ends can send a message at any time they want, and one end sends a message that contains some kind of error message like authentication failed or whatever, and then hangs up, closes the connection. The local end, if it happens to send a message at that time, or try to send a message at that time, it gets an error, econ reset, saying that the other end has closed the socket. On some operating systems, you can still read the goodbye message from the other end, and on some you can't. So this leads to different failure modes where you kind of lose all these error messages on some operating systems, but not others. Actually, Windows is the one that does that. There may be others. So that was kind of an interesting thing I discovered recently. I just added it to my list of tales of strange cross-platform problems and portability problems. I found no solution to that. Yeah. So that is my list of strange portability things that I wanted to talk about. Yeah, it's not a very structured talk. It's just some things that were on my mind. Does anyone have any questions they want to ask me about that, or any other feedback, or share my screen?
So I do have a lot, but maybe first, like, other people would like to ask something. If you can unmute, or you can type your question in the chat, then I will read it.
Oh,
you see
set prop
this
title
comment?
fast. Okay. Yeah. Yeah. Okay. So actually, I think that was my first FreeBSD patch. It was well known that on FreeBSD, when you're running Postgres, you should turn off the set prop title feature, which updates the process title that you can see in top or similar things. Every time you're like, whenever it's doing something different, it would keep updating that. So you could always see which processes are currently in a select or in a commit or whatever else. And that was really slow in FreeBSD because it used to be a system call. And it's kind of like I added a feature to make that fast, like it is on Linux and every other operating system, by making it so you can just write into memory. But that wasn't very clever, because actually I found the code was already there from years and years ago. Someone had changed it to be a system call, so I kind of just changed it back. It wasn't like, but that made some workloads go 10% faster or something, while keeping that feature on. I actually really like that feature where you can see what processes are doing. So it was a nice beginner patch for FreeBSD. So yeah.
If I may actually, because I did like my own test about transparent huge pages like about 1 year ago, and
okay.
You know, it's like I think that they are not like recommended for using with Postgres because of like old bugs that already has been fixed. Because it's been before it's been like a lot of bugs, for instance, like that you know, system is like trying to allocate some pages, so it's scanning the memory and it's like this scanning process is causing much more CPU usage than you can gain back from like using the huge pages. And actually there's been like a lot of bugs there, but I think it's been like pretty well patched, and now it's like now in my test at least it's running a lot faster with transparent huge pages. And actually I've got really a funny case, because I've been actually like investigated a lot of things, and one of them was like if I will use another file system for text logs, for wall logs, of course, how my, you know, how my Postgres will work. And actually separating text logs gave me like much better performance than separating wall logs, which, you know, wall logs are like the first performance advice that everyone gives. And actually I was so surprised that I started to investigate like what's happening, why like separating the text logs are much faster. You know, I got so much better results than like separating wall logs. And you know, and I've seen that a lot less page tables, like I've been like investigating ProTMEMinfo, and page tables with wall separation were like really big, and with transparent were much smaller, and just investigated more parameters, and it turned out that system was starting with the separating log, text log, starting to use transparent huge pages really heavily. And that's why I had this, yeah, that was super strange. So I would never like guess that, right? Why? Yeah, I don't know why, but yeah, I'm sure it has. So because I see that in the metrics. So it was so crazy, but it's really like boosted because of those transparent huge pages. So it's been
That's
wow.
very interesting.
Yeah, and
Which version of Linux was that?
I can check because I've got that on presentation. So CentOS 7, but you know, to give you more like, you know, more details, I can send you that.
Maybe my information is really out of date on Linux transparent user pages. It sounds like it might be.
Yeah, but it was actually some time ago. I've seen like a blog post of Ibrar Ahmed, like he was working for Percona now, and actually he had the same results as me. And it's, I think he published that like last year, so it's like seems to be working.
Yeah, very interesting.
Adam, you don't want to unmute yourself because
yeah,
it's really long.
Yeah, I can unmute myself, but didn't want to forget it, so I typed it down.
Okay.
So there are some factoids, as you spoke about Postgres history, so I will go over them, and there are some actual questions. So one factoid is, did you know that PostgreSQL was originally written in Lisp and was later
because
they found it just too slow. They really wanted to try and do it in Lisp. The other thing is that in their original paper, Stonebreaker says that the process architecture is actually just a quick hack to get the system up and running. And that threads will follow next. So I'm waiting for those threads.
Yeah, it's crazy, isn't it? I mean, it's like
36.
Yeah, it's just crazy. 1986. I mean, that's just crazy. And that's from a time when there were no standard threads, right? So it made sense for them to say that because they would have had to implement it differently for every operating system, which would kind of suck. But yeah, we have no excuse. We totally should do that. Actually, I think it's really interesting that the people who started the Parallel Query project, Robert Haas and I worked on that team until recently, decided that it would be so hard to do threads that it would kill their Parallel Query project if they tried to do that first, even though it would make many things in the Parallel Query project easier. So it was an interesting strategic choice. It probably we will switch to threads sometime in the next few years when somebody decides to really give it a go, and then we can rip out a whole lot of junk and everything will be better.
But the question is, should we go towards threads or to an event-driven model, like with a thread per core and an event?
Yeah, I think that would eventually happen. I mean, we refer to that concept on the Postgres mailing list. People talk about an asynchronous executor. I think we will eventually, which is essentially what you just said. I think we will eventually have that. Yeah, it's probably there might be an intermediate stage which looks more like the thread per connection model or something like that, and then finally a thread per core model would make sense. So one of the steps towards doing that is compiling queries down to a form that allows you to treat them as coroutines. So that at the moment we kind of use the C language stack as we execute queries, right? So you can't really capture the continuation in scheme language, or you can't really pause and then go and do something else because the C language stack is actually involved in the query execution. But if you convert the queries, compile them to another form which has opcodes that are followed or something like that, then you can interrupt, stop processing that because now it needs to wait for some IO and go and run something else instead. And yeah. There's like a whole series of sub-projects required to get to the event-driven model you're talking about.
Yeah, I was also worried on the memory model because right now a lot of the cleanup is done by the OS and the Reaper, right? and now you would have to manually make sure that all those Postgres mallocs are actually freed and not relied on the
I see what you mean.
Exactly the same was like was in the Bruce Mondin talk. Like he pointed out that it would be really hard, like deallocate memory like from the threads because they share like the same memory space.
Well, I mean, one thing that I think comes from the Lisp heritage is that we allocate memory as if there's a garbage collector, and there kind of is a garbage collector, right? There's this memory context concept, which does provide a kind of garbage collection, right? Like we don't just call malloc all the time; we call palloc, and then palloc registers these blocks, and it can free them all. So, it is possible to clean up. It's not as bad as you say.
Okay, about memory and stuff like that, you all probably heard about the famous Linux out-of-memory killer and how like we don't have that problem in BSD. But how many of you do you know? How many of you know about the actual killer that is there and can kill Postgres in an interesting way? There is an out-of-swap space killer.
Out of what? Out of swap?
Out of swap space.
Okay.
So you can run out of swap space, and if Postgres happens to allocate memory, then it will be like killed. So that's a hidden surprise right there.
Yeah. Well, one thing that I'm personally interested in improving in Postgres is having a cap on how much memory you can use, because right now it's kind of there's some control knobs, but it's kind of hard for a human to understand what they mean. And
it's impossible.
Well, I mean, those numbers do get, like workmem does get used for something, but it gets multiplied by many strange hidden variables, right?
Well, workmem is like workmem itself, like set it to 10, but that means 1 times workmem per connection times the planner nodes, because like if you do a complex plan, then each planner node can use up to that many node workmen. And if you have parallel queries, you have to also multiply that by the amount of parallel queries. So we can go up to a gigabyte from 10 gigabytes of workmen with a single query.
Right. It's a pretty good summary.
So to the questions, enough of the questions. So first question is, what record size would you use on ZFS with PostgreSQL? Like, because many people recommend 8 kilobytes or a multiple. And when people recommend 8 kilobytes, they say for better performance because that shares the page size with PostgreSQL. And when people say more than 8 kilobytes, they have in mind better compression on ZFS. Right?
I wouldn't be surprised if there's no single right answer, because some people will be frequently doing large scans, and then it might be better to have a larger record size and better compression. But I don't know. I've run a few databases on ZFS, but honestly, not enough to have a very good opinion on that.
Okay.
I know that the Joyent people, you know who I'm talking about, they gave talks where they showed that they often use 16 kilobytes block sizes, and I don't know exactly why.
Yeah, they also have a interesting post-mortem where they show how they force ZFS to do large block prefetching when out of vacuum scans tables. I think
yes.
that happens sometimes.
Yeah, so they that's right. They had so I've seen a couple of interesting things from those people. One was their post-mortem from that problem. Was it Brian Cantrell? Was it him that wrote the blog? Yeah. He pointed out that it was scanning 1 gigabyte segment files but because we chop very large tables up into 1 gigabyte segment files, the operating system couldn't see the prefetching, which leads me to wonder if we should explicitly issue prefetch requests for sequential scans. Then it would fix that problem, but it still wouldn't fix it for them because Illumos ignores fadvice. So you'd have to use something different than fadvice. But if you that is potentially a solution to that particular problem. But I'm trying to remember. It wasn't that talk that I was thinking of though, or that blog. It was something else. Something from Sean Chittenden, I think it was, that talked about how they used. Yeah, because they worked on a thing called PG Prefalter. Have you seen that?
No, I haven't.
So when you've got a streaming replica and it's receiving the wall from another database node, and the wall contains references to many blocks all over the place, it reads ahead in the wall and faults in those pages so that when Postgres recovery wants to look at all those different random pages all over the place, they're already in the arc in the case of ZFS. I actually did a whole lot of work trying to build that feature into Postgres for Postgres 13, but unfortunately I just missed the deadline and didn't get it in. So I actually have a patch that does exactly that kind of pre-faulting based on ideas from the joint people, from Sean Chittenden, and that's why I was actually rereading all kinds of stuff that he wrote about that, in which he claims that 16 kilobytes was the best size for your block. But all I can do is tell you that that's what he said. I don't know. I don't have a good answer of my own based on research that I've done or anything like that. So,
okay, yeah. I have two final questions with ZFS, and I will give up the airtime. So those last two questions are: what do you think on disabled fsync on ZFS? That's one question. And the second question is, what do you think? Would you disable all compression inside of PostgreSQL when you have a compressible file system like ZFS? So I'm thinking about toast table compression. So when you have large strings, you already have them compressed. And I heard that PostgreSQL has optimized string ops when compression is not in use. So I will let you answer that, and I will go up there.
So the first question, no, you can't turn off fsync just because you're using ZFS, because it means that the data that ZFS decides to write back on its own write back schedule, like every 5 seconds or whatever, may have some dependency on the data that would normally get written back with fsync. You can't. Yeah, it doesn't work if you turn it off. Yeah, I haven't studied that question very carefully. I'm not sure if there's some reason why you think that should work, but yeah, no, I'm pretty sure that doesn't work. I could think about that some more and try and give you a better answer, but my gut feeling is that could definitely eat your data. All right, so, and the second question is disabling compression in Postgres when it's enabled on ZFS. So ZFS probably has better compression just because what's the best compression algorithm on ZFS? It's
CS2D, I think.
Yeah, I don't think what Postgres is using is very good, but I could be wrong about that. I don't know. I think it's possible that it would be better. It's possible, but honestly, I don't know. You'd have to test it. How often do I use dtrace with Postgres?
The question actually is, would you use both, or would you disable one?
I don't know. I'd have to test it. I don't have an answer.
You know, I've been comparing Toast to Xzip, and Toast is really, really poor. So I've got the test result if you want would like to check, but
Mhm.
my God, it's this toast compression is almost like no compression. Like
Yeah,
comparing
I
at
think there's
least
been some.
this, yeah.
Yeah, I think there's been some discussion about changing the compression algorithm, and I think
I,
somehow that
mhm.
discussion got stuck. Um,
Yeah, but you know, it would be really great, like if I could switch for some tables, like please use like a bigger rate of compression, because it's really I've seen people that using PL Python like to only for using gzip, you know, and it's really like saving a lot of storage, like a lot comparing to
yeah,
Toast.
yeah. There was a patch proposed, must have been about a year or two ago, that made it optional, so you could have plug-in compression algorithms, and you could specify which one you want to use. But somehow that patch got
Oh,
stuck. I think it just takes a lot of effort to convince everybody, to agree on things. For one thing, I think there was some fear of a patent problem around one of the algorithms. I've forgotten the details, but
oh,
yeah. But you're right.
okay. I know that Python. Yeah, but I know that Python just using normal, you know, zip. It's just like interface only, you know, this Python for normal OS like zip.
Mhm.
I believe so. Yeah, but okay, I've got another question for Philip on the chat. Can you agree on the simple executive level takeaway message? All other factors equal. Know-how, business environment, etc. If you have a free choice of operating system for your Postgres, prefer Linux over BSD kind of systems?
No, I wouldn't agree with that statement. I
You do prefer Windows, right? It doesn't have overcommit, so.
I mean, personally, I think okay. Personally, I don't want. I don't really like monocultures. I don't really want Linux to be the last operating system. If it's the last operating system, I think it's, I mean, that's a ridiculous idea. I think there are some pretty good reasons to use Linux in real world situations, because it's well understood, and companies might have support contracts for it, and so on. I mean, there's all kinds of practical reasons why people prefer to use Linux, but I think it's not far from being the case that FreeBSD, at least, I don't really know enough about the other BSDs to really comment, but I think FreeBSD is a fine operating system to run a database on. There's a few problems here and there, and in fact, I could give you a long list of complaints of things that could be fixed, and I'd like to think that all of those things can be fixed. Yeah, I think it's a fine system to run a database on. I don't really, yeah, if it really is all other things being equal, the main reason I would say to use Linux would be just for political reasons within a company. You probably don't want to introduce a different operating system if there's already a well-established system, right? So I don't know.
Okay, the other one, will the answer change with KQ and other improvements coming to FreeBSD?
Yeah, well, I mean, I suppose what, this is like a fantasy, right? But I think what I would like to happen is I would like Postgres and FreeBSD to work together so well that they are a better technical choice, right? I mean, if you think about FreeNAS, is pretty popular. A lot of people use that for running, basically as a way to do a file server with a load of ZFS disks or whatever. And for a while, FreeBSD was the best way to use ZFS, I think, or the best open source way to use ZFS. Now I think that edge is probably being lost. Now you can probably use ZFS pretty well on Linux now too. But people were actually, because FreeNAS was so nice to use, people were prepared to use an unusual operating system just to use that one piece of software. And I think it's maybe possible that in the future, Postgres could run on FreeBSD so well that people are prepared to try a different operating system. I don't know, but maybe that's just a fantasy.
Okay. I see that there is probably a comment to Adam's question that you could probably disable full page writes, not fsync.
Yeah, I think that's probably true.
The previous one. Yeah. And Adam, you can ask your own, right? Question.
Yes. So how would you perform fast online snapshot with ZFS or PostgreSQL? So the main point is ZFS is great that you can quickly snapshot the whole database and it can be terabytes of data. But if you snapshot a running database, you get possibly a point of recovery and you will start up in recovery mode and that will take time. You can, of course, checkpoint for doing that, but do you know of any tricks that could reduce the likelihood of snapshotting in the wrong moment? Or maybe could we make Postgres aware that we want to do a file system snapshot, like a patch or something?
Well, anytime you do a file system snapshot, you're going to have to run recovery to recover from it. It's just it's necessary because of the way the system works. Like I mean, Postgres works on the basis of a write-ahead log. So things that have been written to the log that have not yet been flushed to the disk, to the data files, it just has to replay the log, unless there's a shutdown checkpoint. So yeah, I mean, snapshots can't fix that problem.
Okay, I see another one. What would you like to do with your commit bit next? Are
we talking about? Is that referring to Postgres or FreeBSD?
I don't know. Could a person named me answer that?
I can give both answers. So for Postgres, I've got a number of projects that I'm working on at the moment. Oh, okay. Oh, hi. Okay. Cool. So FreeBSD. That is a good question. So firstly, I started working on getting that POSIX fadvice stuff to work for OpenZFS, but that's actually not a FreeBSD thing anymore now, right? So that's kind of weird. Like ZFS has moved out of FreeBSD, so now it's just send pull requests to those guys, and hopefully they commit them, and then eventually it comes back to FreeBSD, right? So so let me think of another thing for FreeBSD. Oh yeah, so yeah, so one area I'm quite interested in is collations and the way that they change. And B-tree indexes in Postgres become corrupted if the order of strings changes. And the order of strings changes sometimes when collations are updated. So, it's not really much of a problem in English because we don't really have very many letters, and there isn't very much to argue about when you compare it with the sort order of letters, because we don't have too many accents or anything on the characters. But in some languages, I have no idea if Polish is one of them, but in some languages, people occasionally decide to change the rules about the sort order of words. I don't really know why they do that, but they do. And so we have this situation where every now and then a new operating system update comes out that changes the sort order for some words, and that causes B-tree indexes to get corrupted. And oh, hi Vic. Yeah. So yeah, so the idea, the potential use for the commit bit next was I wrote a patch to actually keep track of what version each collation is that the operating system provides, and whenever the operating system updates the collation definitions, it just gives you a function you can call to ask it. And then Postgres would call that, and it would learn when the definitions change, and then force you to rebuild your indexes. That's like a feature that I've been working on very slowly as kind of a background job that involves an operating system patch and also a Postgres patch to go with it. That kind of, yeah. So that's my answer to that question. Kind of answers both things at the same time, actually, for both commit bits. So yeah.
Okay. Adam, maybe last question, because I don't want to,
Yeah, right. So in that case, I will skip the one about CFS and PostgreSQL cooperation, because I would like to see something like, for example, Postgres knowing that it can tell the operating system to snapshot now, like something like that.
Mm-hmm.
But the question is, can you tell us about the secret Cabal project on the PostgreSQL wiki?
All right, let me just remind myself what I put on there. So that's
I linked it.
It was really just, yeah. So that's really just a place to write down ideas that I haven't really necessarily had time to do anything about yet, but don't want to lose track of. Yeah, but I also update it when things, it gives a kind of a feeling of progress. Let's see, how many dones are there here? 1, 2, 3, 4, 5, 6. And then not done. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, so there's plenty more things to do. I mean, some of the things I talked about in this talk I mentioned here. Yeah, there's some links to different complaints that I've found around the internet about performance problems on FreeBSD, or there's a few links to issues in the FreeBSD bug tracker and Postgres commit-fest entries and so on. So yeah, basically my ongoing work on trying to get those two things to work together nicely. I try and write about it on there. So feel free to, if anyone wants to get involved in any of these little projects, please, feel free to update that wiki and look at things and write patches, and I don't know. But Adam, you're an OpenBSD guy, right?
Yes, and at work we use PostgreSQL on FreeBSD.
Okay, all right.
I won't tell you how our fsync is enabled or disabled on. but I might use your recording to convince some people.
Actually, for the 1st of April, I've written an email to inside my organization, our organization, that we should turn fsync off, to make it more performant. And I proposed some other stuff, a pluggable API as to DevNull and some stuff to boost performance. But I have to say that not everyone treated that as a joke.
And how many told you that? But we already have it enabled or disabled.
Okay. So actually, we should probably finish. So thank you very much, Thomas. It was super interesting for me, and I think for a lot of the guys that were on the call. So thank you very much for getting up that early. And,
no problem. It was a pleasure.
Great. So it was really great having you here. So good coffee, I think now, right?
Yeah.
Yeah. Thank you a lot, and hope to see you soon.
Cool. All right. Thanks very much.
Yeah. Thank you.
Yeah.
Bye.
Nice to talk, everyone.
Thank you.
Bye. Good night.
Thanks.